Hey everybody, what's up? Hope you guys are having at least a decent day today despite these fearful circumstances. Today in the electrical and computer section of today's FE exam workshop review, we are going to be going over semiconductor properties. We've got about 5 questions here today. And for those of you who are currently taking or have already taken Cal State Long Beach's EE 330 class or analog electronics, this would be a really good supplement for those who are taking the course or have yet to take it, and it's a good review for those who have already taken it. Let's get started. Number 1. A 9-volt battery is connected across a semiconductor with a resistive diffused layer 1 centimeter wide, 10 centimeters long, and 1 centimeter thick. The diffused layer is doped with an N-type dopant to a concentration of 8.34 times 10 to the 17th carries per cubic centimeter. The intrinsic carrier concentration in the diffused layer is 10 to the 10th carriers per cubic centimeter. The mobility of holes is 150 square centimeters per voltage second, and the electron mobility is 360 square centimeters per voltage second. Most nearly, what is the current through the diffused layer? Okay, let's move on to my camera right here so I can label my variables. We've got about 9 volts here. I'm going to create a little separated layer of variables right here. So we have a width of 1 centimeter, a length of 10, a thickness of 1, and then we have what was that concentration for N-types? We have 8.34 times 10 to the 17th. And then the intrinsic carrier is going to be 10 to the 10th. Now we have the mobilities. So the electron mobility. Now keep in mind here, I'm going to be writing as mu n, because electron mobility is more associated with the N-type. And then we have ourselves a hole mobility of 150 squared centimeters per voltage second. And the holes likewise are often associated with the p-types. All right, let's do the mathematics. So one of our key equations here for semiconductors, P and N types, is Pn is going to equal Ni squared. But currently we're missing the concentration of p-type carriers. So since we already have N and Ni, we can simply do Ni squared over N. And then when you crunch in the numbers, you should get an answer of about 1.2 times 10 to the second power carriers per cubic centimeter. Okay, so if we're going to find the current, but we have a voltage, that means we've got to find the resistance. And if we're going to find the resistance, we need to find the resistivity, which is the reciprocal of conductivity. So our conductivity equation is sigma is going to equal Q n mu n plus P mu P. So Q is going to be simply 1.6 times 10 to the negative 19th. Now I've got like a whole bunch of other numbers to fill out here. 0.34 times 10 to the 17th. Okay, and if you crunch all those numbers into your calculator, you should get an answer of about 48.04 Siemens per centimeter. And as mentioned previously, we have a resistivity. Resistivity is the reciprocal of conductivity. Since we have our conductivity, we just need to do P over sigma. Damn notifications. So we get a resistivity of about 0.0208 ohm centimeter. But now we got to find the resistance. This is where our length and width come in. Well, length and width and our thickness. So our sheet resistance is going to be resistivity divided by the thickness. But that's simply just 1 centimeter, and the centimeter unit here is going to cancel out. So we just need to, our answer is simply going to be 0.028 ohms. But now if we're going to find the total resistance of our diffused layer, we have to consider the length-width ratio. And times it by our sheet resistance. So length, width, that's just simply 10. 0.02808. So we have a resistance of about 0.208 ohms. And lastly, if we're going to find the current, we got to use Ohm's law. 9 volts, 0.0208 I. And I is going to be 43.3 amps. So if we look back to the problem here, our answer should be C. All right, we made it to the first problem. Now let's move on to the second one. When placed in a particular electric field, an N-type semiconductor experiences a drift current of about 1 kiloamps per square centimeter. The semiconductor is doped to a concentration of 8.76 times 10 to the 14th carriers per cubic centimeter. The intrinsic carrier concentration is 10 to the 10. The mobility of holes is 490. The mobility of electrons is 1,310. Most clearly, what is the strength of the electric field? All right, let's begin. So our variables are okay, so we have a N concentration of 8.76 times 10 to the 14th. Our intrinsic concentration is 10 to the 10th. So once again, we're going to need to find P. And our mobility, our whole mobility is going to be 490. And our electron mobility is going to be 1310. And our drift current J is going to be 1000. I'll explain it a little bit, but for now, the steps that we are currently undertaking to solve this particular problem, it's going to be the same. Well, it's somewhat the same as problem number 1. So Pn is going to equal Ni squared, but once again, P is missing. And if you crunch that into your calculator, you should get an answer of about 1.14 times 10 to the 5th carriers per cubic centimeter. Once again, we got to find our conductivity. Now, if you crunch all of that into your calculator, you should get a conductivity of about 0.184 Siemens per centimeter. Okay, now this is where, now to reintroduce, or at the very least reinforce why we needed the drift current here, it's essentially to find the strength of the electric field. So your drift current is going to equal your conductivity times your electric field. But we already have our drift current, so it's going to be 1000 is going to equal 0.184 E, and E is going to equal about 5.44 kilovolts per centimeter. Now, if we look back at our problem here, at our answers, your answer should be B for number 2. All right? Okay. Now let's move on to problem number 3. A p-type semiconductor is doped to a concentration of 5.65 times 10 to the 15th carriers per cubic centimeter. The intrinsic carrier concentration is, well, 10 to the 10. The mobility of holes is 460. The mobility of electrons is 1260. And our total drift current, J, produced in a semiconductor is equal to the semiconductor's conductivity, sigma multiplied by the electric field, well, just like in the previous problem. Now, the semiconductor is placed in an electric field with a strength of 75 volts per centimeter. Most nearly, what is the drift current? Oh, excuse the background noise. I will deal with it 1 second. I'll be right back. Okay, sorry about that interruption. Some background noise from a Zoom session I'm also taking part of at the same time. Okay, let's get back to the problem. So I've already listed our variables down as I was reading the problem. So our steps, once again, are going to be the same thing. Actually, essentially, problem number 3 is essentially has the same steps as problem number 2 here. So Pn is going to equal Ni squared. This time, n's missing, so crunch that into your calculator. You should get about 1.77 times 10 to the 4th carriers per cubic centimeter. And once again, our conductivity. Okay, crunch that into your calculator. Your conductivity should be about 1.139 Siemens per centimeter. Wait, did I list J? Oh, sorry about that. Our electric field was 75 volts per centimeter. Sorry about that. So our drift current is going to be J is going to equal sigma times E. So we just got to times 75 times 1.139. Our drift current should be about 85.4 amps per centimeter squared. And if we look back at our choices here, we have C. C should be our answer for number 3. All right, we got 2 more problems. Let's hope you can hang in there. I'm going to read problem number 4 now. A germanium-based N-type semiconductor is doped such that the negative charge carrier density far exceeds the positive charge carrier density. The conductivity of the semiconductor is 0.643 Siemens per centimeter. The intrinsic carrier is 10 to the 10. The mobility is, 2,970. The mobility is 8,860. Most nearly, the electron carrier concentration in the semiconductor is. So now we need to find out what N is. So it's essentially almost like reverse engineering everything we've done so far. Okay. So keep in mind that essentially our N is going to be significantly bigger than P. So when you consider the conductivity, that essentially means that if N is significantly bigger than P, that means this term right here just reduces down to 0. So our total conductivity is going to be strictly N-based. Okay, so now the electron mobility is going to be 8,860. And our total conductivity is 0.643 Siemens per centimeter. Well, this seemed to have taken the work. Well, this took the most of the work out. So given this simplified equation right here, our N is going to simply be sigma divided by Q mu n. And then if you crunch that into your calculator, you should get an n of about 4.53 times 10 to the 14th. If we look back at our choices, our answer is going to be C. All right, last problem. An N-type semiconductor has a dopant concentration of 4.53 times 10 to the 15th cubic centimeters. Damn notifications. So N's going to be 4.53 times 10 to the 15th. An intrinsic carrier of, 10 to the 10. A mobility of holes, mu p, is going to be 460. And the mobility of electrons is 1260. Most nearly, the resistivity of the semiconductor is... Okay, well, basically that is problem number... That's basically problem number 1 with just less steps. Let's do it. So Pn is going to be Ni squared. Also, sorry about the janky use of the camera. Then again, I'm an electrical engineer, not a filmmaker. Okay, so Ni squared is going to be divided by N. So if you crunch that into your calculator, you should get a P of about 2.21 times 10 to the 4th. And now our conductivity. All right, so if you crunch that in, our conductivity should be about 0.9132 Siemens per centimeter. And our last step, our resistivity is going to be the reciprocal of conductivity. So we're going to get something about 1 point something, 1.095. So if we look back at our choices here, our answer should be B. All right, everybody. We went over the properties of semiconductor materials. Hope this was a huge help to you guys. And we're going to be going over another section next week, YouTube style, next week. Hope you guys have a good day. See ya.